This video, we're going to play with Wolfram-Cloud Mathematica and look at a geometric distribution in probability. So a geometric distribution is when you are looking for, you have a number of independent events and you are looking for something to occur the first time. So my example is going to be I'm going to roll dice repeatedly, two dice, six-sided dice, and I'm going to repeatedly roll those dice until I roll a snake eyes, until I roll two ones, until the sum is a two. And then I want to know what's the distribution, what are the characteristics of how many times it takes to roll. So I could roll it straight out on the first roll could be snake eyes, or it could take 100 rolls, and it sometimes does. Okay, so so in general the probability of success, or what you're looking for, the thing that you want to occur for the first time, we're going to take to be p. And then for it to occur in the n plus 1th time, then that probability is p times 1 minus p to the n. Um, so you needed first n quote unquote failures, or um, not getting snake eyes. So that's 1 minus p raised to the n, and then p. So that's sort of first thing we want to do is test that, probability should add up to one. And so I have p times 1 minus p raised to the n, and I'm summing it from n of 0 to infinity. Now the p can be pulled out. I can call the 1 minus p sort of x, and then that is a well-known sum of the geometric sum, hence the name, the geometric series, hence the name geometric distribution. So the geometric distribution is related to a geometric sum series. Okay. And that's a well-known problem that we know how to solve. Um, and so first thing we test, and so I can just say, here's the sum and have Mathematica do it. And it will do that, and I will get a one, as you see I did. Okay. Um, Now we want to start looking at uh, means and variances and things like that. And that ends up bringing down. So if I wanted to find the mean, then I have my probabilities, and then I'm multiplying them by n plus one. Because again, uh, I had n failures and one success. Um, and so it is if n equals zero, then I got snake eyes on my first roll, and etc. So I'm multiplying n plus one here. Um, and so if I want to, if I just take out 1 minus p and think of it as some generic x, then I know that the forgetting the p and forgetting the n plus 1, if I was just summing x to the n from 0 to infinity, that's the well-known geometric series, then I would get uh, 1 over 1 minus x, provided that x is less than 1, which it is here because it's 1 minus p, and p is a probability. So p is between 0 and 1. And so 1 minus p is between 0 and 1, and we're fine. Okay. I can get values of n uh, in x to the n. So I can get an n out front. If I were to take a derivative with respect to x, that would bring down a power, and then I could multiply by an x that would restore the power but bring down the n. And so I can do all these sums, but I'm going to let Mathematica do it for me. So that's sort of my normal philosophy is if I know how to do it, but it's tedious, then let Mathematica do it. And so here was the probability and n plus one. And so altogether that will be the mean. So that's why I called it mu, and that's 1 on p, well-known result for geometric distributions. Um, if I take the expectation n plus 1, and then I'm subtracting 1 on p, which I know to be the mean, then and square that, then I am getting uh, the central moment, the second central moment, or the variance. So, um, and that was 1 minus p on p squared. Um, and that's related to the standard deviation. So another sort of related quantity to the variance is the standard deviation, where I would just take the square root of that. Um, so, and that's another sort of well-known result, and people will often sort of stop there, but I decided to push it further and get the third and fourth central moments, and they are then related to the ideas of skewness and kurtosis. So I put in, if I'm taking my quantity n plus 1 and subtracting my mean and taking the third, that is the third central moment. So I called it CM3. And again, it's just sort of applying x ddx to the result of the geometric series and grinding that out. But there it is, 2 minus 3p plus p squared, all on p cubed. And I can also do it for the fourth central moment. And I got that, or Mathematica got that. Okay. The when you're defining the skewness, uh, they sort of want to scale it in a way so you scale by you're scaling the third moment by the second moment, and if our quantities had some unit, then the third central moment would have those units um, cubed. Let's say we are measuring distances in centimeters or cm, if I call it centimeters. Let's imagine we're in feet or something crazy like that. So if I'm measuring something in feet, this would be feet cubed, and cm2 would be feet squared. But if I take feet squared and raise it to the 3/2 power, then I'm getting something sort of without a unit. So that's sort of that definition. And they're all known. And then I just say simplify. It could simplify more, except it doesn't necessarily want to go to doesn't necessarily want to conclude that my p is positive. So that's why it sort of won't take that sort of squared p out of the denominator square root. So it could be simplified a little bit more, but it is sort of uber careful. The kurtosis, so I call that SQ. Kurtosis, I call KU, and that is the fourth moment divided by the second moment squared. And again, it sort of makes it dimensionless. Okay. And so those are sort of some standard distribution measures, centrality, spread. Is it sort of is it symmetric around the skewness? Is it symmetric? And then kurtosis talks about sort of gets into the tails. Does it? And you often are comparing this to the value for normal distribution, where the kurtosis would be 3. Something like in Excel, if you do kurtosis in Excel, it's doing what they call excess kurtosis, and they subtract off the 3 And when you're doing excess kurtosis, then it goes to zero for normal distribution. But in Wolfram Mathematica, they just do kurtosis, not excess kurtosis. So three would be this would be three would be the kurtosis for normal. This is going to be nowhere near three, as we'll see. Okay. Um, so I have, the only parameter is p. So all these statistical values, the mean, the variance, the skewness, the kurtosis, are all just simple expressions in terms of p. I also, another measure of centrality is the median. And the median is like if I sorted a bunch of values, it is the sort of one in the middle. And so in terms of probabilities, I said take these probabilities and sum them not up to infinity, but up to some value m minus 1. Remember that if I went up to m minus 1, that would have been sort of capital M rolls of my dice, because there's always one more roll because you need that extra event for the success. So this is the number. M minus 1 is the number of failures before the success. So if I'm summing this up to M and setting that equal to 1/2, that is sort of the value at which I have sort of like half the probabilities are done and there still have to go. So that idea of median and the sort of finite truncated geometric series is also sort of standard easy to solve. And so I just ask Mathematica to solve it for my capital M. So how many rolls until I get my success? But I'm looking for the median. Okay. So I have values in terms of P for all those quantities. Now let's do some simulation. And my favorite example is rolling snake eyes. How many times do I roll the dice until I roll snake eyes? And so here is my simulation. I have sort of a while loop inside a for loop. So I have a number of samples. Here I chose 10,000. I'm going to collect the samples. The samples are going to be how many times did I roll the dice until I got snake eyes. So if it took me, 57 times, then 57 would be my first sample. And then the next time I got it on the second roll. So 2 would be my second sample. So I'm collecting samples. So I just have the for method here, setting up my loop over samples. And for each sample, the sum is going to be just the sum of the two dice. So I'm really breaking it down. I could sort of make this look a little bit neater, um, or have a little less typing. But I said the sum, I'm going to sum my two dice. So my sum is 0 because I want to get into my while loop. I'm going to continue rolling dice until my sum is 2. And so I just need some value that's not 2 to get into the loop for the first time. I am counting the number of times I roll. So that's what my counter's for, while my sum's not equal to 2. And I just type the usual sort of computer sciencey programming explanation equals to say not equal, and then this Wolfram-Cloud just sort of changed it into the like not equal symbol. So that's not obviously not on my keyboard, but sort of redefined my explanation equal into this symbol. Getting a random integer, so within this range. So I have the square bracket is my method of random integer. The curly bracket is defining my range. I'm getting a random number inclusive between 1 and 6. I'm getting another one. I'm adding them. I'm incrementing my counter. That's my while loop. I get out of my while loop when I finally get the sum to be 2. And then I append my count to my samples. And so I do that many times. I made a histogram of my samples, and this is the sort of the behavior you expect for a geometric distribution. This sort of very, the sort of one on n behavior, sort of going down. You expect it to be high in the beginning, maybe a little fluctuation here and there because it's a simulation. And we're also letting it decide I just did the simplest histogram, so it's choosing the bins and so on. Okay. And so you have this thing, it's got it's not normal, it's not a normal distribution, it's a geometric distribution. Let's see how we compared to our things above. Let me run it one more time. So 10,000 goes pretty quickly. Then later on, I'm going to start taking samples of my samples, and then it's going to slow down a bit. But just, barely blinked and gave me 10,000 samples. Okay, then there is my histogram. The mean should be about 1 on P, and then I'm setting P to be 1 on 36, and then calculating the numerical value. And so that's a good comparison, 36, 36. What about my variance? The variance is of this order, like 12,000, 13,000. And if I take what I expect from what I calculated above, I'm expecting 1260. Okay, what did I get from my simulation for the skewness of the samples? I got around 2. What am I expecting? This is just me evaluating the sort of exact expression above with a P of 1 on 36 and getting the numerical value. So I'm expecting around 2. I got around 2. And then finally, not finally, the kurtosis. And so that is the kurtosis of the samples. And this is the calculation. So 9.49. This is it's hard to get the kurtosis values very good because that is the one that is going sort of most into the tails. The higher the higher the central moment, the sort of more you're getting out into the tails. Okay. And then here, what is my median? I got a median of 26, and then this was just P. I could put in this. This is the log. They had a minus when they solved it. They had a minus log of 2, which is the same as the log of 1/2. This was P. Let me put it back in as P. 1 on 36, and I'm getting. I'm expecting 24 for my median. 24. I got 26. Okay. And then I just remind myself how to do this. I'm not going to do anything more with P down below, but I just like to remind myself if I wanted to do something with P as a variable after I've given it an explicit value, then I can clear out its value. And then if I say what's mu now, it's not going to give me some number, but it's going to give me 1 on P. Whereas up here, when I had mu, it was substituting in the P, but now I've said forget P, And so it goes back to the variable version. Okay. Now I'll just look a little bit at the sort of sampling distribution. So I have these quantities, I have the mean and the variance and the skewness and the kurtosis. And I didn't do median, sorry about that. But I'm going to, and so here is my for loop with my while loop. So that is a, a single simulation, in this case over 1,000, not 10,000, but 1,000. But then I'm going to repeat that simulation over 1,000 samples. I'm going to do it 200 times. So I'm I'm doing a simulation over 1,000 samples. I am getting the mean. So I'm going to get my samples, but then I'm going to throw them away. So I get 10,000 samples. I calculate some quantities. I throw them away. I start again. But what am I collecting for each sample of 1,000? I'm collecting the mean, the variance, the skewness, and the kurtosis. And so those are what. So I am getting a distribution of a statistical quantity. So this is a sampling distribution. And although the distribution samples, the samples of rolling the dice until I get snake eyes is clearly not a normal distribution. This sample, these samples of the statistical quantity, the sort of sample over the samples over the statistical quantities by the central limit theorem. Those are the things that are supposed to be normally distributed. And now, because I'm doing it 1,000 times, but I'm doing that 1,000 times 200 times, this one takes a little while. And then I want to look at the distribution of my statistical quantities. Okay. So I'm going to take my means. I have a collection, a distribution of my means. And let's look at that. Okay. And now, and I did a fancier histogram than what I did above. I did it as a PDF. So a normal histogram, the y-axis is frequencies. How many times did something occur? But when you work with the PDF, it does a sort of two scalings. It's sort of scales the y-axis and also helps scale, in some sense, the x-axis to sort of correspond to sort of a probability distribution function. Um, so this is no longer frequency, no longer number of times it occurred, but the sort of probability, more about the probability. And then we also wanted some, there's, it picks a bin and you don't want anything depending on the bin thickness that was chosen. So when you say PDF, it sort of scales both X and Y to give it the most independence. So the PDF sort of is not affected if I were to run more samples, or is not affected if I chose different bin size. And it's the thing that's sort of it's the version of the histogram most useful or most easily compared to sort of math, and I want to compare it to normal distribution. So down here, I'm going to plot a normal distribution. A normal distribution has two parameters, the mean and the standard deviation. So I'm taking a normal distribution. I'm giving it the mean. It's first parameter is the mean. I'm going to give it the mean of the mean samples. I'm going to, and for the standard deviation, I'm going to give it the standard deviation of the mean samples, PDF, and X. That turns it into sort of a normal distribution, and I'm plotting it. And then I'm plotting it from the mean minus 3 standard deviations to the mean plus 3 standard deviations, and sort of with normal distributions. 3 standard deviations gives you sort of like most of it. I don't know, 99% or something. So there was that. And then I'm just going to sort of put those two things together. So I just sort of typed it out all over again. Um, but all this really is showing the histogram and that normal distribution together. And we see that that seems to mostly have the right shape. I'd do better if I had either one of my numbers bigger. I could have more sample, either my sample size could be larger, or my number of samples of my samples could be bigger. And this would smooth out a little bit, but you see it does have the basic shape. Whereas the other distribution, again, was not normal. So this is this sort of sampling distribution idea of picking samples of samples, and the samples, even if the original distribution is not normal, the sample of samples tends to go towards a normal distribution. And then there's supposed to be a particular dependence on the number of samples, and I didn't really sort of, I have some things below, but sort of I was reaching the limit of what Mathematica would do for me, so I sort of stopped there. But here's the variance. So this was my statistical quantity of the mean. Here's my statistical quantity of the variance. So same idea. So I've got this normal distribution. I did a number of samples. I got the variance. Then I collected a distribution of variances. And that is, seems to be at least roughly a normal distribution. Same thing for skewness. And same thing for kurtosis. Okay. And then I got an explicit mean of the kurtosis examples. We were expecting this to be around 9, and I got like maybe a standard deviation. Okay, just get those individual values rather than using them as parameters of the normal distribution. And I started to up the number of samples, but I'm probably going to stop here because I wanted to watch it sort of approach that as my number of samples got bigger, my it should be more sharply peaked around the answer. But I was reaching the point where it was pushing Mathematica to its limits. I'm working with the free version, so it was pushing the limit of what it would do for me for free. So I think I will end there. So thank you for your attention.